exciting activity and for inviting me here. It's a pleasure to be here. I'm going to talk, well, the title is there, and let me describe the problem. So, you see, we have an equation where L could be the Laplacian, or it could be, for instance, an operator with a Hardy potential. Although the entire discussion is quite different in the second case, and I probably not have time to touch on that. And okay, and the function g is positive on the, well, it's odd convex positive on the positive axis, and for t, and monotone increasing. So it's an absorption term. Now, what do we mean by a solution of the boundary value problem that we see here? Well, we just mean that it's a solution in the distribution sense for the equation, and that U has what I call an M-boundary trace. It's really the same trace as in the Herglot's theorem for positive harmonic functions. So the definition is, of course, you have to know that U is well defined on the boundary of each such domain Dn, and then it's the limit in measure. You can think of UDS as a measure in omega bar, and H is a continuous function in omega bar, in the closure of omega. In the case of a Lipschitz domain, so most of my talk will be on C2 domains, but part will be on Lipschitz domains. So in the case of Lipschitz domain, you see, this is, of course, the harmonic measure in Dn.
I'm sorry, what is D? D is omega?
Excuse me?
D is the same thing as omega?
I don't have a D. Do I have a D? Ah, yeah, D is the same as omega. I just changed it at some point. Yeah. Okay, what does the absorption effect do? Of course, I'm sure that most of you are acquainted with this, but let me mention it quickly. If G tends to infinity fast enough, as T goes to infinity, then the set of solutions is uniformly bounded in every compact subset of the domain. So I see that D and omega will play around. And a sharp criterion for this to happen is the Keller-Osserman criterion, which is precisely this. This is supposed to be uniform in compact subsets of omega, and then the statement is valid. If it so happens that it is uniform in all omega, the supremum of that expression of the phi here is bounded by bound independent of x. If that happens, then we have that ux is bounded by this expression, which is the inverse function with respect to the t variable. And if U is actually a solution that blows up on the boundary, then you have this inequality from the other side as well. This was proved long ago by Bandle and myself in '92, and recently for Lipschitz domains. In C2 domains, you have more. You actually have the ratio of U to phi tends to 1 at the boundary. And the most simple examples are this. Okay. Now some elementary facts which were proved long ago by Brezis and Strauss, Brezis by himself, and I'm mentioning Brezis and Benilan because part of the work that they did in the 70s was published only late in 2003. Okay, so first, there is always uniqueness, monotonicity, this a priori estimate works, and if you have L1 data, there always is existence. The question is what happens when you have a measure nu. Okay. By the way, much work has been done when also the equation is non-homogeneous, and there are some parallel results and interconnections. Oops, what did I do?
Maybe the laptop went.
What? What happened? Thank you very much. Okay, but since we don't have so much time, I'll just talk about the homogeneous problem, the homogeneous equation. Okay. We say that a positive super solution of the equation, not of the boundary value problem, that's again in the sense of distributions, is moderate if G composed with U times rho is integrable. Rho is the distance to the boundary. So it's easy to prove, and rather well known, that every moderate positive super solution has a measured boundary trace, and in fact there is a maximal, there is a solution which has the same boundary trace as the super solution, so the difference is what's called a potential in a potential theory. It has zero boundary data. And if U is actually a positive solution, then it's moderate if and only if it's dominated by an harmonic function, if and only if it has a measured boundary trace. Sometimes one defines moderate solution by the fact that they are dominated by an harmonic function, but of course it's the same. Now just some notation. We'll say, not notation, but terminology. A measure is good if our boundary value problem has a solution. The nonlinearity, that's to say the function G, is subcritical if our boundary value problem has a solution for every nu. Then we say that the problem is subcritical. Now, what are the main problems here? Incidentally, perhaps I should say just, I'm not going to speak about possible applications and interactions. There are quite a few, and they are well known. Let me mention only one, that there is this connection with the what's called superdiffusion theory, and the connection is that for the equation minus Laplace in U plus U to the Q equals 0, if Q is between 1 and 2, then this is related in the same way as the Laplace equation is related to, let's say, standard diffusions. This is related to super diffusions, and therefore this sort of problem has been studied by probabilists for a long time, but the actual problems that I'm going to describe here have been studied mainly in the last 20-25 years, starting with well, I shouldn't say starting, but anyway, a paper of Dinkin from 91 discussed the relation thoroughly and proposed a number of problems. And they are, in fact, the problems that I am mentioning here. In fact, I remember that I think the paper was in 91, and I think that in 92 he visited in our department, and he proposed to me to think about these questions. Previously, I have been looking at problems related to this equation, but mainly questions like large solutions, asymptotic behavior, and so on. Okay, so the three basic problems. What is a good measure? That's the first question. The question of removable singularities. This means we'll say that I should really say removable singular sets. This really means that if you have a singularity on a certain set that is removable, then any solution, a positive solution that vanishes on the boundary outside that set must be zero. There is no other solution. Now, there are really two degrees of removable singularities, one for moderate solutions and a stronger one for non-moderate solutions. And as I'm going to point out immediately, this is the third problem, classification of positive solutions in terms of their behavior at the boundary. Here, of course, the third problem is directed to the classification of solutions that don't have a boundary trace in the sense that I mentioned, and there are plenty such. There are, for instance, large solutions which blow up everywhere on the boundary, so certainly they don't have a finite measure as a boundary trace. And you have a whole spectrum of possibilities. And the question is really, first of all, how to describe their behavior at the boundary in a proper way. A proper way would mean that this is well defined for every positive solution, and that for every trace, we call it, on the boundary defined here, there would be one and only one solution. So this is sometimes called the trace problem. Now, these problems, in particular for this equation, have been studied in smooth domains for a very long time. The particular problems that I mentioned have been studied essentially since the early 90s. And it was done both by using probability techniques and by analysts who used analytic techniques. And in fact, for this particular equation, these problems have been fully resolved, in part only recently. For more general nonlinearities and non-smooth domains, there are many open questions. Now, the subcritical case is, of course, the easiest one. I'll start with a definition. Now, P here means the convolution with the Poisson kernel for minus Laplacian. So, in other words, P of nu is the harmonic function with this boundary data. If we are in Lipschitz domain, then we have to replace P by the Martin kernel. So we say that a measure is perfect. That's a term that I'm using just for this lecture. Before it was called admissible, but I didn't like it because there are other admissible functions. So the simple statement is that if nu is perfect, then it is good. It's really obvious because the harmonic function P nu is a super solution minus P nu a subsolution, and it's immediate. But the opposite is not true. Not every good measure is perfect. In fact, one can construct L1 functions, which, as we know, are good measures, and usually they are not perfect. So now, considering the equation now in a bounded Lipschitz domain, we have the following result. The basic assumptions on G are those that I mentioned at the beginning. Remember that they include that G with respect to the second variable is convex on R plus, monotone increasing, and so on. But in addition, we also make this assumption. Isn't this this assumption, which the motivation for this really comes from the theory of Schrödinger equations, because this should be Gxu over U, because Gu over U, well, I'll talk about that more later, but the equation can be seen as a Schrödinger equation if you look at minus Laplace in U plus Gu over U times U. And then Gu over U is supposed to be the potential of that equation, and this is a basic assumption.
But you don't put any condition on the count on the constant, just the quadratic singularity potential.
Yeah, yeah. Now, if we had minus 2 plus epsilon, by the way, that's well known for a long time. That's relatively not new. It's already classical, but it's from the 80s. Okay. Well, in this case, with this assumption, the condition that G composed with, well, this is simply the harmonic function with boundary data Dirac at y times an arbitrary constant. So if this is moderate, if this is a moderate super solution, Pxy is a super solution, for every y in delta omega, well, this is the assumption, and this assumption is necessary and sufficient for G to be subcritical. Now, this, I think, is the first result of this kind in Lipschitz domain. It's also the first result where one has not only a sufficient condition, but the condition is also necessary. Excuse me. It's both necessary and sufficient, yes. Now, in another case, the one that I mentioned here, this is a different type of nonlinearity. Beta is greater than -2, so G could blow up at the boundary. But here we look at domains of class C2. Then this condition is necessary, is again necessary and sufficient for subcriticality, but for other reasons. In addition, here we can prove that the solution is stable with respect to weak convergence of the boundary data. And I am not sure if here one has the stability. That is still open. Okay. So this is a very recent result. In fact, so recent that there is only a draft of it. But I hope. Okay. Now, first of all, a simple remark. When you have this sort of relation and G bar is subcritical, then of course G is subcritical. That's easy. Now a little bit about the history. In a paper by Gmira and Veron a sufficient condition was given in C2 domains. This condition is similar to SC, to the condition here. In the case, I mean, it's not this condition, but it can be shown to be equivalent to the condition SC when G is independent of the boundary data. In the special case GT equal T to the power Q, the subcritical nonlinearity is T to the power Q when Q is between 1 and critical Q, which is n plus 1 over n minus 1. I forget to mention perhaps that omega is a domain in Rn. In this special case, they also prove that the condition is necessary. Then for this case, result was proved here, some other results later on. Okay. Except for the results in the work with Bakhta, all of the previous results are included in the previous theorem part 2. Okay, I will not have time to describe any sort of ideas of proof. I do want to describe some ideas of proof for a later result, which we'll get to at the end. Now, the characterization of good measures. First of all, this is obviously closely connected to the question of removable sets, because suppose that you have a measure which is supported in a removable set, then obviously you'll not have a solution for it. Therefore, determining what are the removable sets is in a way a question that precedes the other. So in the case of the equation EQ, and now I'm going to talk about the equation EQ. Let me remind you that that is this equation. So for the time being, this is the equation that we are looking at. So in this case, this is the criterion for removability. If the capacity, now C2 over QQ prime is the capacity associated with the Besov space W W2 over Q prime on delta omega, where Q prime is this. And this condition is sharp in the sense that if you have a set F with positive capacity, then you can find measures supported on that set for which are good measures, which are in fact perfect measures. Now, once we know this, the good measures can now be characterized like this. The boundary value has a solution, that's to say nu is a good measure. If nu is absolutely continuous with respect to this capacity. This means that when a set on which the capacity is 0, then nu will be 0. Now, when you have so first of all, it's clear that this is a necessary condition, because if you talk about positive measures, if you have a solution, if nu is good, any solution, positive solution dominated by nu is automatically good. So if nu were positive on a set of capacity 0, then its restriction to that set would be good, and it cannot be good. So this is a necessary condition, that's obvious. To prove that it's sufficient, one has to show, well, one shows by using a certain theory of approximation of measures, you can show that if nu vanishes on such sets, then you can approximate it by monotone increasing sequence of perfect measures. Since the perfect measures are good, and the monotone increasing sequence in this case will give you in the limit a solution, you will have that. This particular result for C2 over QQ prime and in general for, yeah, I think essentially for this was proved by Barat and Pierre for some work that they did on these problems, but for non-homogeneous equations. And it was also previously done by Fayel and de la Pradelle with some differences, and Dalmasso, but all of them were for this type of capacity, Bessel capacities, let's call them. Okay, now these two results, it took quite some time to establish them, and they were established for Q between 1, this is greater than 1, not equal, just greater than 1. This was established for Q greater than 1, less than or equal to 2, by probabilistic techniques, by Legal, Dynkin, and Kuznetsov. Dynkin and Kuznetsov worked together, and in parallel by analytic methods for any Q greater than 1. Okay. Recently, both of these results have been extended to general nonlinearities and in Lipschitz domains, that's in a work with Ancona, where we assume this assumption which you already saw before, which allows us to introduce the theory of Schrödinger equation.
Ancona is Alano Ancona?
Alano Ancona. This condition, which appears perhaps a little strange, it's actually valid for a large class of nonlinearities. Certainly it includes all nonlinearities of almost all nonlinearities of this type when H satisfies the Keller-Osserman condition. I say almost all and not all because indeed, for instance, for the case GT equal T to the power Q, we know that every positive solution is bounded by this. This is the Keller-Osserman criterion in this particular case. So here you immediately see that u to the power q minus 1 is less than or equal to a constant times rho to the power minus 2. Now, this is, as I say, true for almost every h there and beta greater than 0 when the Keller-Osserman condition holds. What is the exception if it grows too slowly? And this is, for instance, an exception if you have something like t times logarithm 1 plus t to the power alpha, alpha greater than 2. If alpha is less than 2, the Keller-Osserman condition doesn't hold anyway. But if it's greater than 2, the Keller-Osserman condition holds. This, if you make the computation, doesn't. All right. So that's why I say almost every function. And there is a sharp condition on G that implies star. It really follows from the Keller-Osserman estimates and the other estimates that I mentioned at the beginning. Okay, so assuming this condition, the results A and B here go over to the case of a general equation. That's to say, we look at the equation minus Laplacian u plus gxu equals 0. And we have the following fact, that A and B remain valid with respect to this equation if you replace the Bessel capacity by an appropriate capacity, which we call Cg delta, and is defined like this. K is the Martin kernel, K tau is the convolution with the Martin kernel. Tau is just a positive measure on the boundary. So the supremum of this, these are really perfect measures, you see. So perfect measures normalized in this way, and you take the supremum of all these measures restricted to F. This gives you the capacity of F. It reduces to the Bessel capacity if you have T to the power Q and the C2 domain. Okay, so with this definition of capacity, results A and B remain true, just as stated. Just replace C2 over QQ prime by that capacity. An important point here is that C, excuse me, is the first positive eigenfunction. This is instead of the distance to the boundary, because in a Lipschitz domain, the first eigenfunction is not equivalent to the distance to the boundary, and this is really what one needs, the first eigenfunction. Okay, one point I mentioned before when I talked about the results in C2 domains, that we had to use there the Barain-Pierre theorem. So here, of course, the Barain-Pierre theorem doesn't apply, but...
Let me ask you a question,
yeah.
my ignorance. You go from the harmonic extension to the Martin curve, right? Does it imply a lot of difference? In the normal case,
yeah,
you have a good domain,
right,
you use the Poisson curve.
right.
In this case, you use the Martin curve.
Yeah, well, first of all, in a C2 domain, the Poisson kernel is up to a constant the same as the Martin kernel.
What are
Well,
the
not up to
difficulties?
you have to normalize it
So
at
what
the
are
point
the difficulties?
x0.
What are the difficulties of this case when you have Martin curve? Is this
Well,
much
first of
difficult?
all, in order to represent a function, a harmonic function with given boundary that in a Lipschitz domain, the Poisson kernel wouldn't work. You need this kernel.
Okay.
And this kernel, okay.
I mean, I only wanted to know if this is a technology that is very different.
That is?
Technology that is different from the Poisson, very different.
Well, you don't have the estimates that you normally have.
Because they are weighted by psi.
Not only that, but because they depend on just how GU or V more generally, if you look at the equation minus Laplacian U plus VU equal to 0,
Yes.
then it depends on how V behaves near the boundary. If it blows up on the boundary,
Oh, so
the
ellipsis
behavior
points
is not
have-
at all like the
can give
Poisson
rise to
kernel.
bad potentials in the Schrödinger
Right.
approximation.
So yeah,
Okay, okay, thank you. Okay, so it's a kind of Schrödinger point of view.
yes, that's exactly the Schrödinger point of
Good.
view. Okay, so to prove our results, among other things, we needed an extension of the result of Barai and Pierre that I mentioned before. And we proved that indeed that sort of result holds for general capacities for measures that are absolutely continuous with respect to a large family of capacities, which includes CG delta. Now we have talked up to now about bounded measures as boundary data. I now want to look at the case where the boundary data is given by unbounded measures. And again, I'll start in the subcritical case.
To go back to nice domains?
Here I will discuss nice domains. Yeah. So not only nice domains, but I even discussed the equation minus Laplace nu plus u to the q equals 0. Okay, so you may recall that this is the definition of a model. This is the condition for a solution or super solution to be moderate in the case of equation EQ. Perhaps I should leave this equation here. Oh, well, it's written here. This is EQ. All right. Now, motivated by this, one may define the boundary trace of a solution which is not moderate in the following way. First of all, we'll say that a point on the boundary is regular if it has a neighborhood where u is moderate. Okay? And it is singular if it's not regular. Let's denote by R. The RU is obviously open because Q is a neighborhood. And its complement then is on the boundary is a closed subset of the boundary. So this is the set of regular points. This is the set of singular points. On the set of regular points, we have a measure boundary trace. Just as usual, it will not be a bounded measure. It will be a radon measure, but it's there. On the other, we can simply consider the function, the trace as a measure mu bar, which is infinity on the singular set and radon on the regular set. And the set, so for every couple F mu, F a closed set, mu a radon measure, positive radon measure on the complement of F on the boundary, we can construct such a function, such a measure mu bar, and the set of such measures we denote by B rank. All right. Well, with this definition, it was proved long ago that the boundary value problem has a unique solution. And this was the first time, almost the first time, when uniqueness was proved for boundary values with non-bounded data. So why not the first time? First of all, of course, in the case where the boundary data is identically infinity, this was discussed a lot. These are the large solutions about which there is a very large body of work, and the uniqueness has been proved there under very general conditions on the domain. But this sort of theorem was proved first, previously by Legal. In 95, in the case Q equal 2 and in the plane for Q equal 2. He gave a definition of trace which is probabilistic, and to this day I cannot compare them directly, but indirectly they are obviously the same. And he proved precisely these results in the case Q equal to N equal 2. And he used what's called the Wiener snake technique, which he invented, and it's extremely useful, but it applies only to Q equal 2. Now, I could say 2 words about here the main thing is the proof of uniqueness. The existence is rather easy to do. And the uniqueness is essentially based on the following thing. First of all, you prove that for each such mu there is a smallest solution and there is a biggest solution. And then you observe that if you look at solutions where mu is just 0 infinity, doesn't take any out, then the difference between the maximum and the minimum is the largest. Therefore, it's sufficient to prove uniqueness in that case. That's to say, you can, for uniqueness, you can throw out the part of the boundary measure which is on the regular part. And the next step is to show that the maximal solution is less than a constant times the minimal solution. And it turns out that once you have that, using the convexity, this is not just for you, Q this part, you get that they must be the same. Okay. Okay, here I mention what I already said. In 97, so just a year after this, Legal showed by an example that uniqueness fails in the supercritical case. That was a bit of a shock. And so it became obvious that one needs a description of the behavior at the boundary trace that it's more refined than the one given before. So first of all, let me mention in this context, we'll immediately use the concept in here. Dynkin introduced this concept, sigma moderate solution. This is a solution which is the limit of an increasing sequence of moderate solutions. You can imagine that for such solutions, it's not too difficult to describe the boundary trace. It would be essentially the limit of the boundary traces of the moderate solutions. After Legal's observations, so 2 different definitions of boundary trace were proposed, one by Dynkin, and that should be Kuznetsov, for Q less than 2 and greater or equal QC. The critical value belongs to the supercritical part. And later, for every Q greater than QC, for sigma moderate solution, it's very easy to see that the 2 definitions are agree, not completely up to a set of capacity 0, but a set of capacity 0 is anyway negligible for our problem, so that doesn't matter. And later, Verbitsky showed that, in fact, the 2 definitions agree in this sense up to a set of capacity 0 for every positive solution. And with these definitions, which I will not describe because it will take too long, it was possible to show, as I say, for sigma moderate solution, the definition is essentially obvious. And in general, it's a little complicated, we leave it. So with either of these two, it was proved that the boundary value problem for EQ has a unique solution in the family of sigma moderate solutions. This was proof for Dinking and Kuznetsov. I wonder why I make this mistake consistently. Probably I just copied it. In 1998 for Q less than or equal to 2, and by us in, well, 2004, 2007, because it was really written in 2004 and it was presented in 2004, but it appeared in a proceedings of the Brazil Fest of that year, and that took 3 years. Yeah, so in the class of sigma moderate solution, everything is fine. So the next question is, the complete classification depends on this question. Are all positive solutions sigma moderate? Essentially, the crucial step here would be, can there be a solution whose boundary behavior does not dominate a moderate solution? That there is no positive moderate solution under it. Can there be a solution, a positive solution, which has no moderate solution under it? All right, this is an easily formulated question, but it turned out to be difficult. For the next statements, I need one more concept, and that's the concept of maximal solution. Take any compact subset of the boundary, denote by script UF the family of solutions that vanish on delta omega outside F, denote by UF the supremum. Thanks to Keller-Osserman, UF is obviously a solution, and it can be shown that it too vanishes on the complement of F. Therefore, UF itself belongs to this script F family, and then UF is called the maximal solution relative to F. Okay, so here comes the story of how the question was answered. The first answer was given by Messelati, a student of Legal, who in his PhD thesis published in 2002 proved the result for Q equal to and every n greater or equal to 3, proved that every positive solution is sigma moderate. Again, he used the Wiener snake technique. That's why it's just for Q equal 2. And in general, it's a very probabilistic proof, but combined with some analytic techniques. This was really, at least in our little community, this was big news at the time, and very encouraging too. Now, 1 year later, we proved that for every compact set, the maximal solution that I described before is sigma moderate. To prove that, we had to establish some estimates for maximal solutions, which I defined before, from above and below, and they have this. They can be, I mean, there is an expression which is a little bit like the Wiener expression in terms of, but here in terms of the capacity W, C2Q prime. And it's a long expression which I will not mention, and it's from above and from below, with different constants, of course. That's why I say sharp capacitary estimates, and that's what we used in order to prove this result. In effect, what we showed using such capacitary estimates is the following. There is among the in addition to the maximal solution UF, you have one other kind of, let's call the candidate for maximal solution, and that's the supremum of all moderate solutions whose boundary support is in F. That a priori is smaller than UF, but using these estimates, we could prove again that capital UF is less than or equal to a constant this other function, and as I said before, this immediately gives equality. And now we should realize that every boundary trace is composed of a part where the solution blows up and the part where it's essentially moderate. The part where it's moderate, it's of course a part on which it's sigma moderate. So if this is sigma moderate, the only question is how do you manage to put them together? And that turned out to be quite complicated. But in 2004, Dinkin proved for Q less than 2, less than or equal to 2, that every positive solution is sigma moderate, and he used the technique of Messalati and our result mentioned there. Essentially, he extended part of the Wiener-Snake technique from Q equal 2 to Q less than 2. Well, and quite a bit later, it was proved that the answer is yes, every positive solution is sigma moderate for every Q greater or equal than the critical value. And if I may have a few more minutes. So about this, I wanted to give some very brief remarks about the proof. Incidentally, the proof of Dinkin is a book of about 140 pages. The proof of Messalati, which was in the memoirs, it's only 100 pages. This, I think, it's a little shorter, the last one. So the proof falls into two main parts. For every supercritical Q. So first of all, we answer this question that I said is the crucial question. If you have a positive solution, does it dominate a positive moderate solution? This was the first part, to show that there is at least what to talk about. And then once you prove that, you look at the supremum of all G moderate solutions dominated by the given solution U. This is obviously sigma moderate, easy to prove that it's sigma moderate, perhaps I shouldn't say obviously, but easy to prove that it's sigma moderate. It's of course less than or equal to U, and it can be proved that it is equal to U. And for the first part, which is really the most challenging part, the main idea of the proof is really to reduce everything. So you take V to be U to the, U is a given solution. And you look at U to the power Q minus 1, as I mentioned before, satisfies this basic condition. Well, it's written there too. Therefore, one can apply classical results on Schrödinger equations, and among these, there is a result due to Ancona from 87, which is a representation theorem. Now, the representation theorem under certain abstract conditions was known for a long time. It was proved by Martin. The question was, do these conditions work in a Lipschitz domain and with V of with a potential V of this type, which is of the worst type, that it's less than a constant over the distance to the power minus 2. And this was Ancona's achievement. If it behaves better than that, then this was known. But for this limiting case, it's his proof. Okay, so once you have this, and nu is just a positive finite measure in this case on the boundary, but it's not in terms of Poisson kernel, but in terms of the Martin kernel associated with LV, with the Schrödinger operator. Now, in our case, it can be shown that nu actually vanishes on sets of capacity 0. Nu is not the trace. It has nothing to do with the trace. It's a finite measure. The trace is not finite in this case, but nu is a finite measure. But still, it can be shown that nu vanishes on sets of capacity 0, and therefore, in this case, one could use just Barat and Pierre to get that it is the limit of an increasing sequence of measures in this space, and this space is precisely the space of perfect measures. Then the next crucial step was to prove the following, that if you have a perfect measure tau, and you take the minimum between u and the harmonic function with trace tau, then either it's positive or tau is a singular relative to nu. Now, if it is positive, it means that you have under u a solution with boundary trace tau, because p tau is a good super solution, and you can construct under it a solution with the same trace tau, so you answered the first question. Now, going back, we have here that nu n increases to nu, and nu n is a perfect measure, so we can apply this thing to nu n. And if we apply this thing to nu n, we come to the conclusion that the minimum is positive because nu n is less than or equal. Is less than or p nu n is less than or equal to the. Well, no, I should say differently. Nu n is less than or equal to nu, so it's certainly not singular with respect to nu or tau, and therefore the minimum must be positive. So this proves the first step, and the second step relies, among other things, on the fact that I already mentioned that the maximal solution is sigma mod. That's all I can say today. Thank you.
Questions or comments?
Can you remind again what is the QC, the critical index?
What's the critical index?
QC.
Yeah, it's the value is just this, and so for q less than this, every measure is good, and for q greater than this, well, there is a criterion for good measures.
So this is the critical exponent in dimension n-1.
Excuse me?
It's the critical exponent in dimension n-1.
No, it's in dimension n. The boundary is in dimension n-1.
I mean the Sobolev exponent.
Yeah.
No, it's not Sobolev. I mean the one in the Yamabe.
It's n plus 2 over n minus. It's
No, that's n plus 2
over n minus 2.
over n minus 2. It's not the
Selling
same.
exponent of n plus 1.
Right. All right. Okay.
Anything else?
So when you have one of these measures that you don't know what to do with her, if you regularize and solve, can you get some of projection or something?
Well,
like a good measure that is below?
yes, and we, first of all, if we are talking about finite measures, and there are lots of measures which are not good, then indeed there is a procedure to get the best, the largest good measure dominated by it, and this is a work with Brezis and Ponce in 2000, in Agosto, in 2004, I
You
believe.
did in the domain. This work works also on the boundary. Formations
Ah,
on the boundary.
that part was done in the interior, you are correct, but the main ideas work also on the boundary, and it's really not very different. Same can be done with parabolic problems, because of course all of this has a parallel for initial value or initial boundary value of parabolic problems.
I have another question. Yeah. You have written a book.
Right.
Now the question is everything that you say
No,
here?
it's only the subcritical case. I intend to write a continuation on the supercritical case.
I mean, okay, so we have to read the book and then begin with this. This is a book with Veron.
With Veron, yes.
Has appeared this year.
It appeared at the end of the previous year, I believe. Yeah.
Okay, but
And
this supercritical thing is new. The supercritical thing is new. Okay.
well, the last part is from 2012, and the part with Ancona is from 2013. So, yeah.
If we want to understand the basics of these measures, capacities, everything about this problem, everything is there in the book, right? In the first part.
In
I
the
understand.
future book, not in the existing book, because in the subcritical case you don't need the capacity. In that case, you see, the capacity underlines a sort of topology, which is called the fine topology, which we use. Now, the fine topology in the subcritical case, for instance, is just the Euclidean topology, so you don't need the capacity.
Okay.
Yeah.
Nothing else? Well, let's thank the speaker again.
Thank you for your attention.
So why do you do negative propaganda?
Oh, we resume at 3:15.
Negative?
Why